go ahead and, as an exercise, practice exercise later, not right now, you would go ahead and do a refutation resolution proof for this statement using a set of support strategy. And you can post those answers to Piazza if you want to. We can go through it. But this is, this is the kind of form I would expect you to be able to do on the final exam. I mean, I would give it to you in clause form and you wouldn't have to do any translation. First order planning. Let's talk a bit about, unless we talk about this after break some more, I probably won't test you on this, but it's really quite a bit more powerful than propositional planning was. I had even thought about jumping ahead and doing this first so that your project could be a first order planner rather than a propositional planner, but that's okay. The representation of operators, you probably recognize this general representation of operators. Just for the purposes of this treatment, I'll just be talking about these strip style operators that we talked about in propositional planning. You have a precondition list. And in this case, we're going to be thinking about a kind of robotic domain, which I introduced when we talked about propositional planning. You've got blocks on a table, you've got a robot hand, and you've got a set of goal conditions. And these goal conditions don't completely specify the world, they just specify the particular conditions that you want to be true when this is done. So the table isn't shown here because, in fact, if there was a block D here, it would satisfy the goal conditions if A was on B, was on C, was on D. That would also satisfy the goal conditions. But for this very simple domain, which is called the blocks world domain, we represent this. You can pick up an arbitrary block so long as it's on the table and it's clear there's nothing on it and the robot hand is empty. And the effects are going to be to negate some conditions. In the original strips, these were called delete conditions. You made them untrue. Once you pick up a block, it's no longer on the table, it's no longer clear, and the robot hand is not empty. And some conditions are made true, holding. The block is now being held. There are a number of operators here putting down a block, again, on a table. And what's interesting about this, at least in part, is the way that they've engineered the operators here, or the way these operators have been engineered. There's a difference between picking something up from a table and picking something up from another block. And that has to do with the effects and how you represent these operators. You could rewrite this domain in a way that there was no distinction between picking up and unstacking, or putting down and stacking blocks, but there would be some other complications of the domain if you did that. So strips operators look like this. To unstacks, one block has got to be, the block that you're unstacking from another has got to be on that other block. And so here's one approach to planning. There are many approaches to planning, first order planning. But let's say this is the initial state. C is on A is on the table, B is on the table, nothing on B, nothing on C, and the robot hand is empty, and these are the goal conditions. In a regression planner, you would start by looking for those operators that can achieve one or more of the goal conditions, called sub-goals. So if we take a look at the original operators, one way of achieving A on B is to apply stack A on B. And remember that stack A on B is not, there are no particular There are no constants in there. And so what you're going to have to do is you would look, if you wanted to achieve this condition, you would look through the list of operators for those which had a effect which unified with what you wanted to achieve. And unlike in refutation theorem proving, it should not be a negated effect, but it should be a effect that leaves this true. And so if you want to achieve on AB, stack is the one operator in the collection that has a condition on XY that will unify with on AB. And you would do that unification, you would bind X to A and Y to B, and you would apply those substitutions throughout the stack operator. This would be the operator after applying those substitutions. This particular planning system might then, there's a number of ways you could do it. If you were following a depth-first approach, you might actually seek to ensure that this stack operator can be achieved before looking to see if on BC can be achieved. But in this particular case, the way that we can achieve on BC is through the stack BC operator. And again, we bind on BC to stack XY. X is bound to B, Y is bound to C. We apply the substitutions throughout, and that's what we're left with. We have some tentative links that support. Clear B is supported by the initial state. Clear C is supported by the initial state. These are called tentative supports because further planning may cause these supports to vanish, and you would have to achieve them through some other means. But these, holding A and holding B, are not yet achieved. And so we pick another operator, again, looking at the effects that will unify with one or more of the conditions that we want to achieve. In this case, the preconditions for stack AB, and holding A is 1. So we would bind X in this case to A, and we would apply those substitutions throughout for the pickup operator. Same thing with pickup B, holding B. Clear A is a precondition for pickup A, and if we go back and you'll notice that clear A is not one of the conditions here. There's something on A if you go back and look at the original visualization. Unstack X from A is one way of achieving clear A. And so what I did is, or what Tweak would do, is it would go through and it would look at the effects of all the operators, looking for those operators with an effect that unified with a precondition of pickup A. In this case, the substitution is incomplete because to unify clear A with clear X down here, we just have to bind one of the variables, Y in this case, to A. And we apply that substitution throughout, and you'll notice that X is currently unbound. There's no binding of X there, just A. So the task here is now to get whatever is on A off of A. The process continues for, in this case, quite some time. In this case, we can find that all of the preconditions for unstack are unifiable with conditions that are specified in the initial state with the appropriate bindings. Once Tweak has found the necessary operators, it can do some reordering. Actually, some of you did this for the project. You sort of find the operators that you need, and then you do a search for the way to order them. In this case, one way to order these is to stack BC, the hand empty there is what is supporting that hand empty there. And once you establish that as a link, and again, this is part of a big search space, so this is all going to be looking down one path of a state space search. But one operator would be use that hand empty to support that hand empty, and that determines an ordering, that stack should come before that pickup. And we can continue, and what we are left with is a particular ordering based on these supports. And there is that ordering that we use to support the plan. So this is a total ordering. I'm going to sort of race through this other one. This other plan is one that illustrates partial ordering. In some planning systems, the planning system will come up with a total ordering. You saw this in propositional planning too. That is a perfect specification of the ordering of the operators. But in a lot of cases, it's you don't want a total ordering. You would like a partial ordering, and then at runtime, when the plan is actually being executed. Remember, this is all the robots thinking about what it's going to do before doing it. But if you can specify a plan with a partial ordering, that is, construct that tower semi-independently of that tower. That is, swap those two blocks, There is no requirement that you swap C and D before A and B or vice versa. So you want a plan. In this case, it's possible to build a plan which is a partial ordering. I'm just going to show you a little animation. If you missed it, you can see it online. There's a couple of problems here if I do ask you to, if we decide to do something with planning with first order logic after the break, I'll have you revisit these slides, and here's you've got a couple practice problems in which you can try them. A lot of planners would fail on a situation like this because of an imperfect memory. If this is the initial state and you want to swap the contents of A and B, or of registers P and Q, a lot of planners would be too opportunistic. They would write B over A and then not have A available as part of the plan to complete it. So there are some planners, some old planners, that could not solve this simple problem of swapping locations. You need a third register, of course, to do that swap, but and that stems from over-optimism. That is, or lack of foresight. They would overwrite one value by another and then lose that other value, and so the plan would fail. Just want to touch on relational learning. It's very different than, in some ways, than the propositional learning that we've talked about, both decision trees and, most kinds of learning which are in vogue now are propositional learners. They learn from feature sets or feature vectors, which in some ways is a very impoverished representation. It's not a sophisticated representation. It's been a representation that's been around forever. But in relational learning, you don't have feature vector representations. There's not that rigid format for the representation of objects. So here I've shown a very intuitive example of what we might hope to learn through relational learning. If you've got a card of one rank and another card of the same rank and three other cards of a different rank but all the same, and the cards are not the same, then you have a full house in poker. And this might be a representation of a full house. So if you wanted a machine to either play poker or learn to play poker, and in part of that learning, learn what legal hands were, this might be a rule that you would either give the system or you would expect the system to learn from observing others playing poker. And so it's still pretty much a supervised learning task. That is, your system is observing poker play, and somebody gives a hand, identifies it as a full house. That label then becomes gives the system information from which it can learn. Here are two full houses, two separate full houses, and it's easy to see that these are full houses because I've sorted them conveniently for you. These are both full houses too, though, and I have not sorted them so conveniently. In general, if I was to learn about full houses and I was to take a look at this sorting, if the sorting was to be given to me in a computer system, or me, or a human learner, in a way that made the pattern that was being learned apparent, then learning would be aided. If the appearance or presentation of the object, or two objects, in this case the two hands, was not presented in a fortuitous way, learning might be more difficult. If we could depend on an instructor, a supervisor, presenting the instances in a convenient way, then what I could do in this ordering is, I was told basically that this was the mapping. This was the mapping that was important in learning a full house. I'd look across these two, these cards, pairs, using this mapping, and I would apply generalization operators to them. And I'll show you an example of that in a moment. But if it's unfortuitous, if I cannot rely on an instructor that's going to be good and present things in a way that makes learning simpler, then I would have to look at all possible orderings, or many possible orderings of mappings between these two decks, or two hands of cards. So I might consider this mapping, I might consider that mapping, that mapping, that mapping, that mapping, but I might be forced to consider this mapping and that correspondence within that mapping. And I might be forced to consider a mapping that placed this in correspondence with that, and this in correspondence with that. But you might have to consider a whole bunch of different orderings or mappings to actually learn what you wanted to learn. Here's another possible example. This is a representation I might have for a straight. Same kind of thing here. Card one has a rank. In this case, you look at these and they all have different cards, different ranks. But what's important here is that rank one is immediately follows rank two. Rank two immediately follows rank three. Rank three immediately follows rank four, etc. If that is satisfied, then you have a straight. And again, learning, the instructor might be kind and give you and indicate that you're going to be given these examples in particular ways from which generalization can occur. But in general, again, the computer might have to deal, and you and I might have to deal with unfortuitous presentations that would make learning more difficult, because I would have to consider many ways of mapping cards in this hand with cards in this hand if I wanted to do generalization. So here's an example of what I mean by that. This is, say, a couple of positive examples of a full house. This generalization of those two hands stems from a assumed mapping of one after the other. That is, using the mapping that's apparent in this presentation. So this card and this card are in correspondence. This card and this card, this card and this card, this card and this card. And this is my representation of the generalization from those two hands. And it's a particular way of generalizing. In this case, just like we had substitution lists in resolution, we have association lists that are similar but differently intended in relational learning. So when I put these two in correspondence, the Q and the 6 are placed in correspondence, and the hearts and the spades are placed in correspondence. And so I've got an association list that includes Q6 and H spades. Now these are different constants, okay? They're going to generalize to a variable. And so in the case of the heads spades, I have replaced that variable by S1. And I've replaced Q and 6 with R1 rank. Now I go to the next pair of cards and I again see a Q6. Q6 is an association that I've seen before. So I don't create a new association, but I use the variable that I assign to that association, which is still R1. Here I have a club heart. This is not an association that I've seen before. And so I don't use the variable that I used in suit, the suit for this generalized card, but I introduce a new variable, S of 2. And when I go to these, I associate 5 and 7. I have not seen 5 and 7 before. So I assign a new variable to represent that 5-7 association. And I do the same thing here. When I get to this association, notice that the suits are the same in this case. And so in the case where I've got matching constants, I leave that matching constant alone. So this is almost, just having seen two instances, this is almost a perfect representation of the generalization of a full house, but not quite. It's a little bit too specific. It says you've got to have a club amongst the 3 alike ranked cards. There's going to be many branches here in this generalization tree because if I've got an instructor who's not being kind, I've got to look at many associations. Here this is the association that matches these two things. Notice that this relates a 6 and a 5 and a spade and a spade. So I replace that with a variable rank 1, but the spade, the constant remains the same. For this next one, I look at this association, 6 and queen, but the hearts match. I've not seen this association between 6 and queen before, and so the rank is a different variable than this, but the constants remain the same. And here I've arranged this so that the suits in this case really distinguish this generalization from the other generalization. In this case, I had placed 7 and 5 in association, and here in this last mapping, I placed 7 and 5 in association. I've seen that before, and so this rank is the same as this rank. But these are two, having seen only these two card hands and not being assured of or not knowing about the the presentation policies of the instructor, these would be two valid generalizations for these two hands. And a machine learner would have to look at all those possibilities in order to decide which was more likely. And it would continue learning. So the next instance of a full house would be used to generalize both of those two instances. But you can see how this becomes a search problem too. These are just two immediate children of this first instance of learning. As other instances, positive instances of full house and even negative instances of full house are used. You can use both positive instances to and negative instances to continue this search and to hone the definition of relational definitions. I've got some other material on macros in first order logic. I'd like you to go through these slides. We did talk about macros in propositional logic. The idea here is very much the same. We might complete a plan. So let's say that we've actually completed a plan, and this is the set of operators that will go from here to here. But there are ways to generalize this plan so that it doesn't just apply to problems that involve blocks A and B and C, but it can be more widely applicable. And that can be done through generalization of the plan in particular.